Hello everyone. Today we will look at chapter 9, which is hypothesis testing. And chapter 9 will be about single population, and next chapter will be about double population. So in single population, we'll look at a single claim about a population parameter. And as we know, like the basic parameters are the mean, the proportion, or they could be standard deviation. Now, standard deviation is beyond our subject. So in this chapter, we will look at the population mean, and we will look at the population proportion. So mean is like a number. So, for example, the monthly cell phone bill, how much is it? And proportion is a ratio. It's between 0 and 1. So, for example, the proportion of adults with cell phones, 0.88. Now, in hypothesis testing, first we need to define what is the null hypothesis. I0. I0 is the hypothesis that we are trying to test. So, for example, what is the average number of TV sets in a home? Like, for example, in my home we have 2 TVs, and maybe the average is 3. But can we test it? Now, in a null hypothesis, the most important thing when defining a null hypothesis is to include an equal sign. This could be like exactly equal, it could be less than or equal to, it could be greater than or equal to. But in a hypothesis testing, first we define I0 where there is a sort of equal sign. So the null hypothesis begins with the assumption that the null hypothesis is true. It should always contain either an equal sign, less than or equal to sign, greater than or equal to sign. It may or may not be rejected. Now, when you have the null hypothesis, obviously you will have an alternative. If the null hypothesis is equal to, then the null hypothesis will be not equal to. Now, as a rule, that the alternative hypothesis should not contain the equal sign, less than or equal to sign, or greater than or equal to sign. Those are the terms reserved for the null hypothesis. So, if the null hypothesis, let's say I0, has equal sign, the alternative hypothesis, let's say H1, will have not equal to sign. Now, if the null hypothesis has less than or equal to sign, the alternative will be greater than. If the null hypothesis has greater than or equal to sign, the alternative will be less than. So they are completing each other, and they are the opposite of each other. So here's an example. There's a claim that the population mean age is 50. So this is the claim. And if you put into hypothesis, that means the null hypothesis, I0, is that mu equals 50. But we do not know the population. So from this population, we choose a sample. And we check if the sample mean is somewhat in line with the hypothesis. For example, if the sample mean is 20 and you have a hypothesis of 50, that's very unlikely that it's true. So you will reject the null hypothesis. But let's say if the mean was, let's say 45, 50 might have been acceptable. But that depends on of course, the calculations. So in calculations, one thing important is the level of significance, or alpha. Alpha defines the rejection region. And alpha is also called the level of significance. Now, if you remember, in confidence interval, we created confidence intervals for 99% confidence, 95% confidence, and 90%. And this alpha is the opposite of confidence. It becomes like significance. So if it is 99% confidence interval, then alpha will be 0.01. If it is 95% confidence level, alpha will be 0.05. If it is 90% confidence level, alpha will be 0.10. 0.10, for example, means 10%. So 90% plus 10%, the total should always be equal to 1. This is by definition. The probability, by definition, the maximum probability is 1. So here's an example. In the first one, we are testing with whether the mean equals to 0. So this is equal to. If it is equal to, that means it's a two-sided hypothesis. And the rejection region will be both the left side and the right side. And both areas are equal to alpha over 2. If you add them up, that will be alpha. Now, let's check the second one. The null hypothesis is that the mu is less than or equal to 3. Now, the alternative means greater than 3. So we are looking for the higher than level. And that part is the rejection region again. Again, this area, the probability of rejection is alpha. And the third one is whether the mu is greater than or equal to 3. In that case, the rejection region will be mu less than 3. And we are looking at the lower tail test. So again, this is one tail test. And the tail test gives us the area. For example, since the first one is a two-tail test, we have this area as the rejection region and also this area as the rejection region. Now the second one is upper tail test, so we only have the upper area as the rejection region, and this one is the lower tail test, so we have the lower side as the rejection region. Now, how do we formally test the mean of a normal distribution? This is one of the most common testings that we are looking for. What is the mean? Now, if sigma is known, and we will assume that it is known, then we can use the Z distribution. Now, if sigma is unknown, we will have to use the T distribution. But as you know, if the sample size is large enough, the T distribution will converge to the Z distribution. And to keep things simple for this course, we will assume that the sigma is known, and we will use the T distribution. Now here's a test. Normally, in terms of testing, things get quite unusual depending on whose choice is that. But I will personally choose that if the alternative is greater than, that means I star will be less than or equal to. It's how it should be. Less than or equal to. Because this is one-sided test. And what we do is we apply this rejection rule. We reject I0 after calculating a z value. And this is called the z, say, calculated. It's something that we calculate using our calculator. Here, x bar is something that we calculate from the sample. The mu0 is the hypothesized value, which actually comes from here. This mu0 is the same as this mu0. They are the same. Now, sigma, we assume that it is known, but in many cases it will not be known. In any case, if the standard deviation is large enough, we can assume that S is the same as sigma. So this is also going to, in our case, this will also come from the sample. Although it says population here, but for our course, we will assume that it's from the sample. And square root of n, this is also from the sample size. And we check if this condition is satisfied. On the right side, you see this z alpha values here. The z alpha. Now, this value, the most common values for, I think, 90%, it is 1.64. For 95%, that's 1.96, and for 99% is 2.56 something. Let me see what's the number. or maybe 675. I think it's 675. So here's the decision rule. First, you convert the hypothesis into some sort of like a Z distribution. The Z distribution is simply attained by subtracting the hypothesized value from the sample mean divided by standard deviation over square root of n. This is one way to look at it. The alternative rule is to reject I0 if the x bar is greater than mu0 plus z alpha times sigma over square root of n. But in many cases, this is a bit complicated. This one is easier. So make this conversion and check with the appropriate z value, and then if this condition is satisfied, reject I0. If it is not satisfied, so this area is the rejection region. If it is on the other side, then you do not reject I0. So the other side means these areas. So here, what we do is we do not reject. So this area is the do not reject area, and this little area here is the rejection region. Now, in statistical packages, there's another way. Statistical packages calculate the p-value. So they convert the sample result into a test statistic and obtain the relevant p-value. The p-value is something like probability, actually. What's the probability of rejecting that? And if that probability is high, or if that probability is actually the p-value, this is opposite, sorry. If the p-value is less than alpha, then you reject S0. If the p-value is greater than or equal to alpha, do not reject S0. So now you might be wondering, what is alpha? We defined 90%, 95%, 99%, but this is for the confidence. For the significance, the alpha is usually used as like 001, that's for 99%, or it could be like 0.05, that's for 95%, or it could be 0.10, that's for 90%. So if the calculated p-value is less than like whatever number that you have chosen, then you reject S0. So here's an example. You have a storyline. In the story, you are testing a claim. Now, what is the claim? The claim here is the average is over 52. Is that correct or not? Now, you put that claim into the alternative hypothesis. And the default is that the average is not over 52. Alternative is that the average is greater than 52. We also know the sigma. So what's missing here? We need to know the sample size. So before the sample size, we are choosing an alpha. We have chosen 0.10. And this is a one-sided test. So for the one-sided test, actually 0.10, the appropriate z-value is 1.28. So we check and reject S0 if the z-value that we calculate is higher than 1.28. And we obtain a sample. The sample size is 64. And the sample mean is 53.1. So we put the numbers. 53.1 comes here. That 52 was the hypothesis. And 10 is the sigma that we already know from here. And 64 is the sample size. And we find 0.88. But this is actually a small number. It's supposed to be higher than 1.28, so that we reject. In that case, we do not reject because our value is not in the rejection region. So since we do not reject, that means there is not sufficient evidence that the mean bill is over 52. Another alternative is to use the p-value. So the p-value approach is a bit complicated. Its formulas are kind of easy if you have like one-sided, but in two-sided it gets complicated. But this is one-sided. So the probability that x is greater or equal to 53.1, given that mu equals 52. So what's that probability? You convert this into z, and it becomes that probability z is higher than 0.88, and that probability is 0.1894. So the p-value that we calculate is 0.1894. But to reject, we have chosen an alpha 0.10. So since our p-value that we calculated is higher than the alpha, we do not reject S0. So one-tail test is where the alternative has only one tail. We have the upper tail test. In an upper tail test, the alternative is that the mu is higher than the hypothesized value. We also have a lower tail test. In a lower tail test, the mu is less than the hypothesized value. So the idea is pretty much the same. In an upper tail test, you choose an alpha, like this could be 0.1, 0.05, or 0.01, and you find the appropriate critical Z value, the critical value for the relevant alpha, and you reject I0 if the calculated Z value is higher than the critical value. Now for the lower tail test, it is the opposite. It's on the negative side actually. If the calculated Z value is less than the critical value from the table, that you use the table to find Z alpha, then you reject I0. Now, the two-tail test, we have two tails. And if it's either on the upper side or the lower side, but this time it's alpha over 2, alpha over 2. Now, the numbers that I have given was relevant for the two-tail test. So the critical values for the two-tail test for 95% confidence level, this will be, the number here will be 1.96, and the number here will be minus 1.96. That is the difference. So here's an example. It's a two-sided example. So we are checking for whether the mean is equal to 3 or not equal to 3. And we have chosen the desired level of significance, 0.05, and the sample size is 100. So let's just check this one. The test statistic is the z value here. X bar from the sample is 2.84. The hypothesized value was 3. The sigma was given as 0.8. The sample size is 100. And we find this value to be minus 0.2. Now this is actually very much at the border. So if the number that you find is minus 2, it could be rejected or not rejected depending on the alpha. For alpha equals 0.05, the critical value is plus minus 1.96. So we have this critical value, the lower critical value, and the upper critical value here. And the number that we found was minus 2, which is like almost at the border, but it's in the rejection region. So since the number to Z value that we calculated is less than the critical Z value from the table, the test statistic is in the rejection region. So what we do is we reject I0. So we reject the null hypothesis and conclude that there is sufficient evidence that the mean number of TVs is not equal to 3. Actually, 3 is quite high. You know, in my house we have 2 TVs, so 2 is a perfect number here actually. Now, if we had chosen this, if we had decided to test this hypothesis using the p-value, Now, first again, we still calculate z values, and from the calculated z values, we try to find the appropriate p values from the table, and the sum of these two values, 0.228 and 0.2228, is equal to 0.0456. Now, if alpha is 0.5, we reject h0 because this number is less than alpha. If alpha is 0.1, we also reject h0. But if we had chosen alpha to be 0.01, then we wouldn't reject h0. So the idea is that whether you reject the hypothesis or not depends on which alpha you have chosen. So we compare the p-value with the alpha, and based on this, if the p-value is less than alpha, we reject h0. If the p-value is greater than or equal to alpha, then we do not reject h0. And in the previous example, the alpha was 0.05, and we calculated the p-value to be 0.045. So that means we reject the null hypothesis. Now the same things apply to the proportion, but this time the way that we calculate the z value changes. Now it depends on the proportion. Now the proportion is a number between 0 and 1. It's the number of successes in the sample divided by the sample size. And we will assume that our sample is large enough, so we can use a normal distribution. In that case, instead of mu, we write the p. Instead of sigma, we can define the standard deviation as p times 1 minus p over n in square root. And the associated z value, now it's equal to the p hat, which comes from the sample, minus p0, which is what you hypothesize, over p0 times 1 minus p0 over square root of n, over n. Everything is in square root. And here's a simple example that there's a hypothesis that 8% comes from mailing. So in that case, the hypothesized value, the p0, is given as 0.08. This is what we are trying to test. And to test this, we look for 500 responses. Like so. So we survey 500 people, we get 25 responses. Our alpha is 0.05. So let's try to make use of those numbers. Now first, the sample size. The sample size is equal to 500. Now the proportion from the sample is equal to 25 over 500. And I think this is 0.05. And alpha is also 0.05. So put those numbers here, put them into the z statistic. So 0.05 minus the hypothesized value over the standard deviation calculated from this formula. So we find this number to be minus 2.47. So we find it to be minus 2.47, but actually this is in rejection region. So we reject the null hypothesis. So there's sufficient evidence to reject the company's claim of 8% response rate. Actually, response rate is very likely to be around like 5%, 6% maybe, because we already defined 5%. So that's it for the hypothesis testing. In the next video, we will go a bit more advanced into hypothesis testing.